So yeah, so we started to discuss the idea of the DDIM, which was basically the generalization of the ddpm. So surprisingly, while we are basically making lots of the changes in the fold process, at the end, like what we are seeing is that there is basically nothing we need to do. It's even just like using the noise predictor. Even you don't need to train the noise predictor again with the new default process, and you can just directly use the noise predictor of the ddpm to run the reverse process of the DDIM. And even the reverse process of the ddpm and the DDIM are basically the same, except for that we are having different distribution for this specific, the posterior distribution. For the cases that we are sampling the xt minus 1 from the xt and the x0. So basically what we are doing for the ddpm is that given each of the noisy data point xt, from the noise prediction, we first get the prediction of the x0 for each of the steps. So which is basically having some kind of some blurry the final the output, the images. And based on that, like we are basically calculating the mean of this specific mean of that the likelihood distribution. And based on that, we are basically sampling from the Gaussian, right? So this was basically the procedure that you also need to implement in the ddpm the assignment. And what we are seeing is that in the DDIM, we are also basically doing the same thing, basically having the same type of the variational distribution for the reverse the process. But the only thing is that the Gaussian distribution, the mean and the variance, these two are basically changed. So here, still we can basically compute the prediction of the x0 from the xt and the epsilon d prediction. But now the mean is basically changed into this formulation. And based on that, we can also still sample from the Gaussian. So the only difference is that we are basically changing only the one line. There will be really like one line change of the code in your the assignment as well, which is basically having different mean and the variance here. Then obviously, like this is basically some kind of the explanation, like how exactly we are computing the mean here, right? So given the xt and the epsilon prediction, we first get the output of the x0, the prediction, which is the output of this formula that we also discussed last time, and getting the mean as well. And obviously, we can consider like skipping like the computation of the x0. So from the relationship across the xt and the x0 and the epsilon t that we keep discussing, we can also directly compute the mean from the xt and the epsilon there, right? So I recommend you to also try to derive those things yourself and see how exactly these formulations are basically derived. So in the ddpm, we could basically directly compute the mean using the xt and the epsilon here. We can do the same thing in the DDIM as well. The only thing is that now the mean computation becomes slightly more complicated, but still basically involving the xt and the noise prediction to compute the mean here. So check out like how exactly these formulations are basically derived. So without basically deriving those things yourself, that will be just like implementing the code based on the pseudocode that you don't understand, right? Then actually there will be some challenges in terms of understanding the lectures from the rest of the class. So I recommend you to basically also try to derive those things yourself. So also the thing is that you also need to see like how exactly ddpm and DDIM are basically related to each other. So as we also discussed last time, DDIM is basically the generalization of the ddpm, and we can see that actually we preset the variance into this form, then we can see the ddpm also becomes the special case of the DDIM, and also then the DDIM also becomes the Markovian process, not the non-Markovian process. So we discussed this idea of like this controlling the stochasticity. So depending on how we set the variance, we can make it to be the same as the ddpm. And also the very interesting part here is that now we can make the whole reverse process as kind of the deterministic process. So there is nothing basically sampling the noise here. So if we make like this sigma to be 0, then we can just strictly use this mean, which means that once we basically sample the x capital T, the sample from the prior distribution, the final output that we're gonna get, the x0, will be determined from the initial sample of the x capital T. So the mapping from the x capital T and the x0 is basically determined. It's not basically changed over time through this kind of stochastic. So that was basically the way that we can basically have some kind of the mapping between the x capital T to the x0, making whole the process to be deterministic. And the things that we didn't discuss last time was basically that, So we know that the minimum value of the variance is basically 0, right? So that's the case that we are making the whole process to be deterministic. Then what's the kind of the maximum value of the sigma t here? So the thing is that if we go back to the formulation of like this posterior distribution, then we can see that we are basically having this term, right? The root of like 1 minus the output, the bar t minus 1 and the minus the square the variance here. So if we basically set the number which is greater than this, then this basically becomes some kind of invalid formulation, right? So from this formulation, actually, we can see that the maximum value of the sigma t becomes the root of the 1 minus the alpha power the t minus 1. So this is basically showing the kind of the range in terms of how we can control the stochastic. So if we set the sigma here into this value, then we are basically having the full stochastic, making the most like stochastic kind of the cases in the reverse process. If we set this to be 0, then it becomes deterministic. So basically changing this stochastic. Yeah, and also what we also discussed last time is that we can now consider accelerating the reverse process. As we discussed last time, the kind of the drawback of the diffusion model is that it's kind of the trade-off. Basically, as we have some kind of the more iterative process, we are seeing that we are gradually denoising the data point and getting some kind of the more realistic data points at the end. Basically, one way that we can basically boost up this kind of computation is to skip some of the time step, basically having some kind of the time interval in terms of like, reducing the number of the time steps in the reverse process. But as we basically decrease the number of the steps, we're gonna get the results, which is basically not exactly following the data distribution that we learned. So that would be the case that the output is basically slightly deviated from the original data distribution, which is basically getting some kind of the slightly lower quality of the outputs. But the interesting some kind of observation empirically is that as we make this kind of the reverse process to be more deterministic in the DDIM formulation, we can see that actually the quality degradation with the fewer number of the time steps becomes like mitigated. So actually, I also don't know whether this is kind of like some kind of proved kind of things, or but my understanding was basically that this is more about some empirical observations. You can also test this out in the assignment too as well. So yeah, so this is basically the summary for the DDIM. So basically, we can see that DDIM is the generalization of the ddpm. So which also means that ddpm is a like special case, the DDIM. And also, the really good thing of the DDIM is that you don't need to train the noise predictor, basically separate the noise predictor. So once you basically have the pre-trained the noise predictor for the ddpm, then you can just directly use that for your the DDIM, the reverse process. So this is really the important defect about the DDIM. So which means that in your the second assignment, you can consider using the noise predictor that you trained for the first assignment to run the reverse process of the DDIM in the second assignment. So that's what you need to do in the second assignment. And also the reverse process becomes deterministic when the variance becomes 0. And this is also very important part in terms of the quality degradation with the fewer number of the time steps becomes mitigated when the variance is small. So this is the table that we have seen last time. So basically, this the parameter the eta here is basically showing some kind of stochastic from the full deterministic to the full stochastic, right? And we are also decreasing the time step from the 1,000 to 10 here. So obviously, like as we decrease number of the time steps, we are seeing that the output, the quality of the output, the generated the images are basically getting the worse. So these are the FID scores, which means that the higher is better. So as we basically get some kind of the higher the FID score, which means that the quality of the image is worse. And we are decreasing when we decrease the number of time steps, we are seeing that the FID increases a lot when it's like the full stochastic case, when it's the ddpm. But in the DDIM, the deterministic case, even when we basically set the time steps to be D10, the increase of the FID is not that significant compared to the case of the ddpm. And even we are getting the even better results for the deterministic case when the time step is the 1,000. So this is kind of the recap of the DDIM that we discussed last time. And the things that you'll need to do, and also our detail will explain about the assignment 2 is that assignment 2 is basically nothing basically but changing your the ddpm code that you implemented in the assignment 1 into the DDIM, which means that before you start the assignment 2, you will first need to finish your assignment 1. So there's the dependency between the 1 and 2. But the 2 will be easier than the 1, right? So, yeah, so that's why we are also extending the deadline for the assignment 1. So before you start the assignment 2, please finish implementing the ddpm code in the assignment 1, and based on that you can start the assignment 2. So, and also the thing is that this code for the assignment 1 and 2 will be also used for the assignment 6 and 7. So there's also the dependencies between across them. So it means that you need to really have some good code for the ddpm, the DDIM here. Any questions about DDIM? Okay. Oh, yeah. So the assignment 2 will be quite simple, but I recommend you to really play with the code and see whether the stochasticity really basically affects this kind of the quality degradation, the mitigation of the quality degradation when you basically decrease the time steps.
Right. Will we discuss like the FID score and other kinds of evaluation metrics in class, or should we like put them up and?
Yeah, that's a really good point. I will try to introduce those metrics sometime in next class or sometime. Yeah, that's a really good question. So actually the kind of one of the challenges for the research of the generative models is basically how we are going to assess the quality of the outputs. So there have been some kind of the ideas for that. FID is also one of the ideas for that, but nothing is perfect. There are many kind of issues in terms of which metric is really good and bad. So everyone is basically using the FID, the fetched insertion distance, for the evaluation of the diffusion models and degenerate models. But you will see that actually this is also not that kind of the best metric. So yeah, this is really good points. I will also try to introduce those kind of the metrics in the class. Any questions? So don't be upset when you get some kind of the bad FID. While we are basically having some kind of criteria for the assignment with the FID, but actually FID is not giving some kind of the big meaning for your degenerate models. So that's why also we set the bar for the FID with some kind of the margins. Any other questions? So actually the plan for this class is that, so we discuss some kind of the very basics about diffusion models like ddpm, DDIM, those things. They're like very basic things to basically discuss many other kind of things. So from the next week, what we are going to do is that we will now going to switch the gear a little bit, and we will start to discuss some more kind of like applications of the diffusion models, basically what we can do. Not just only with like generating images, but more than that. So we're gonna discuss some kind of the applications and more the practical kind of things in terms like how we can also train the diffusion model with the billions of the images. So the typically diffusion models that we can see, like this stable diffusion, mid journey, like those things are basically trained with the 5.7 billions of the images. It's literally like billions of images. So that's why we're also getting some kind of the very, very high quality of the outputs. So we are going to discuss like some kind of basic ideas in terms of like how we can train the diffusion models with this kind of like tons of images, and based on those kind of the pre-trained diffusion models, what we can do in many kind of the applications. So we are going to discuss those kind of applications for like next like few weeks. And after that, we are going to come back to more like theoretical kind of the aspect in terms of like how we can also improve the speed of the computation and how we can also get some kind of better quality of the images by just slightly changing the formulations in the diffusion models. So that's the plan. Okay. So speaking to that, actually, what we are going to especially discuss from the next week is about some conditional generation. So what we have discussed so far was basically just like pure image generation, like whatever images that we have. But what if we have some kind of the input that we have? So like, let's say we want to generate not any kind of the random images, but the dog images. But we might also want to generate some kind of cat images or like human images, whatever kind of images. So when you have this kind of some sort of input, which is basically giving some kind of condition for the outputs that we want to generate. So how we can basically convert our diffusion model into some kind of the conditional diffusion model. So this is like one topic that we are going to discuss from the next week. And this is also the parts of the second assignment. So I'm going to very briefly introduce this idea for today, and then we can also discuss more the details from the Monday class. So here the question is that let's say we are having some kind of some image labels like dog or like cat, whatever kind of things. So given this kind of condition, how we can basically make some kind of images that is like based on this kind of condition. So you will see basically that it's basically a matter of like we are injecting this kind of input into our denoising predictor, and there can be like tons of the way in terms of how we can exactly have this kind of like additional input. So it's basically really kind of the implementation kind of issues in terms of like how we can make the neural network predicting the noise to take not only the XT, but also some kind of the extract input, which becomes the condition. So in this case, that would be basically image labels, but there can be also some kind of the text description for the images, or it can be some kind of some conditional the images or the sketches, the depths, whatever kind of things. So it's the matter of like how we are exactly implementing this kind of some noise prediction in network. And some kind of the idea is that even we can train the noise prediction in network in terms of that it can basically choose taking the condition or not taking the condition. So we can consider like having both the conditional diffusion models, which is taking the image label as kind of input, and making some unconditional diffusion models, which is just generating any arbitrary images. So how we can combine this kind of the two diffusion models, like conditional and the unconditional cases. And the very simple, the practical idea, so you can see that these are just like very practical things, is that like we are basically introducing some kind of the null label. So it's like matter of like what you choose that kind of null label, right? For example, like if we are having the like 10 image labels, then we can basically index them from the like 1, 2, 3, 4 to the 10, right? And we can set the 0 as kind of the null label. So if we basically put the 0 in as kind of the condition, then this is the case that we want to generate like any of the kind of images. But for the cases like when you set some kind of specific the index of the label, then we want to generate that specific images in that class. So that's kind of like very simple the idea in terms of like combining some kind of the conditional diffusion models and the unconditional diffusion models. Clear? And one also kind of extension of this is that we can think about like somehow enhancing the condition that we have. So let's say like we can control like how much the output of the images to look like like the dog, for example. So we want to make some like more like dog images. So you see like what's the meaning of like making some more doggy like the images here. But basically we can think about like extrapolating basically the noise, which is basically predicted with the condition and predicted with null condition. And if we basically extrapolate this kind of the two noise, we can consider basically enhancing the condition that we want to basically put. So if you see this formulation, this first part is basically the noise that we are predicting with our condition the y here, and this is basically the noise that we are predicting without any condition. Basically, just we are feeding the null the label there. And if we basically do some kind of the extrapolation from this to from the null the condition into the image label that we have, then we are basically enhancing the condition more. So in terms of getting the results like this. So what we are seeing is that if we set this like the W to be 0, so if we go back to the formulation here, if the W is basically 0, then we are just purely using this, right? No enhancement, just directly using the noise with the predicted with the condition. Then you can see that basically, yeah, it looks like the dog here I know that is the species of the dog, like Malamus or something. I don't know exactly the name of the dogs, but you can see that it looks like that specific kind of the species of the dog here. But there are some kind of like some variations. So it's not really basically aligned with the condition that we are providing. But basically, as we enhance the condition more and more and more by increasing the W here, basically it's like pushing more into this noise. So we are basically increasing the W here in terms of that we are increasing this noise from the noise that we are predicting with the null condition. You can see the results that we are basically getting the results, which is like really getting that specific the types of the dog. So that's basically very practical, the idea in terms like enhancing the condition in terms of some conditional degeneration. So I didn't explain like what's the meaning of like having this kind of the formulation. So we're gonna get into more details like in terms of what's the meaning of like this. Actually, the meaning is also not that kind of special here. But we're gonna also discuss more about basically how we can make some kind of the conditional diffusion models in many kind of different aspects next week. So the good thing of like this, the simplicity idea, which is called the classifier-free guidance, we can also see like why is it called the classifier-free guidance? But basically the kind of some kind of the advantages like having this idea is that it's very easy to implement. It's just like matter of like having the null the label for the unconditional case and just by doing some kind of the extrapolation. So it's very easy to implement. And also the thing is that it can be applied to the any types of the condition. It doesn't need to be some kind of the text, the labels, the image labels, but it can be some kind of the text description, or it can be some kind of some conditional images, like the sketches, whatever kind of things. It can be even sound, for like sound to image generation for many kind of cases. So we're gonna also see some of the applications in terms of where we can basically apply this idea for some conditional degeneration. The only downside is that now it takes like more time in the reverse process because like we need to predict the noise twice for the conditional case and the unconditional case. So which means that we need to like run the feedforward of the neural network for twice. So this basically will increase the computation time in the reverse process. So these are the pros and the cons of some conditional generation. So also the one of the part of the second assignment will be also extending your DDI implementation in terms like incorporating this condition in a way that you can basically produce the images with like these three classes, the wildfire, cat, and the dogs. And we're gonna also provide the data for that. So this is about the second assignment.
Used by the name classifier-free guidance. Like, why is it classifier-free if you use conditional prediction?
Yeah, so this is the also one of the things we're going to discuss next week. So before we discuss this idea, we're gonna discuss the idea of like classifier guidance. So when you have some kind of some classifier of like all the images, how we can utilize this kind of classifier for like some condition to improve the quality of the image generation. So that was the first idea. And even that idea was not about really some kind of some conditional generation. It was actually more about like improving the quality of the output images. And that idea has been basically extended to this case, which is not having any classifier. So that's why it's called the classifier-free guidance. Without any kind of classifier, even you can basically improve the quality of the images while also basically enabling this kind of some conditional generation. So this was like very simple, the practical idea without that much kind of some theoretical guarantees. But yeah, very practical the ideas. And all this kind of the text to image generation, the diffusion models and stable diffusion, those things are basically implemented with this kind of this idea. So you see that this is really the basic idea. But there are also many other kind of some kind of interesting ideas in terms of incorporating the conditions in many different cases. Any other questions? So yeah, so as you can see, the assignment 2 will be about basically converting your ddpm code into DDIM, just like running the DDIM, the reverse process, and also implementing the CFG, this kind of conditional generation in terms of like taking these three types, the image labels. That will be the assignment 2. No questions. So if there is no question, then our team will take over discuss the second assignment.